In this video we study a powerful primitive in distributed computing, the so-called shared coin. A shared coin is a distributed algorithm that, using the randomness of individual nodes, enables the nodes to throw a collective random coin so that the outcome of the shared coin toss is 0 at all nodes with constant probability and 1 at all nodes with constant probability. Note that these probabilities do not have to sum up to 1, that is, the shared coin toss is allowed to fail. But since it only fails with constant probability 2, only a constant number of shared coin tosses is required for the nodes to get a valid coin toss. Since it is not so easy to implement a shared coin, we start with a simple model where the nodes have access to a global blackboard. The nodes can write arbitrary things to the blackboard at any time. Anything written to the blackboard stays there. At any point in time, the nodes can also read the entire blackboard and get a snapshot of the current content on the blackboard. We are now going to build a shared coin using the blackboard. We call the outcomes of the coin tosses -1 and +1 for reasons that will become apparent soon. So, the nodes generate coin tosses locally and write the outcome to the blackboard. After writing the result of a coin toss, the nodes all read the blackboard and count how many numbers they see on the blackboard. In the example here, all of them read 3 numbers. The nodes continue in this fashion until there are n squared, that is, 9 numbers on the blackboard. Note that the nodes are not synchronized at all, so it is possible that only the node on the left is active for some time, generating another coin toss, writing the result to the blackboard, and then reading the blackboard again. After that, it happens that the node on the left and the one in the middle generate and write another coin toss outcome to the blackboard. They read the board after both new numbers have been written, and so they both now see 6 numbers on the board. Let's fast forward now a little bit. As we can see here, the node on the right was suddenly very active as it now wrote more numbers to the blackboard than the other nodes. Assume that the middle node and the node on the right have just written numbers to the blackboard and so they now read it again. They both see that there are 9 numbers on the board, which is exactly the threshold n squared as we have 3 nodes in this example. Since the threshold has been reached, the nodes sum up the values on the blackboard. If the sum is greater than 0, they declare that the outcome of the shared coin toss is 1. Otherwise, the outcome is 0. In the example here, the sum is 3 and so the 2 nodes accept 1 as the outcome. What about the node on the left? When this node becomes active again, it writes another number, say -1 to the blackboard, and reads the blackboard. Since there are now 10 numbers on the blackboard, it also calculates the sum, which is now 2. This sum is still greater than 0, so this node accepts 1 as the outcome as well. As we can see, all nodes have the same outcome, so the shared coin toss was successful. But why did it work? And how likely is it that the shared coin algorithm is successful? In order to answer these questions, we need the help of the central limit theorem. More specifically, we need to know how likely it is that the sum of independent random variables that are -1 and 1 with equal probability exceeds a certain number. For our algorithm, the random variable x denotes the sum of all numbers on the blackboard. If we set capital N to n squared and z to 1, we get that the probability that the sum of values on the blackboard is at least n or at most -n with a probability of more than 15% after n squared random numbers have been written to the blackboard. In either case, all nodes will see the same outcome because at most n-1 additional numbers are written to the blackboard, which is not enough to change the outcome. So, we can conclude that the probability that all nodes get a 0 or 1 is both greater than 15%, which means that it is a valid shared coin algorithm. Of course, the algorithm has one major flaw. It uses a global shared blackboard, which is typically not available in distributed systems. Can we implement the same functionality using standard message passing? Let's see how this can be done. As an example, we use a distributed system with 5 nodes, but instead of showing the actions and messages of all nodes, we focus on just one node, V. It will be easier to see what is happening and all nodes behave the same way anyway. As in the Blackboard algorithm, every node starts with a write operation, followed by a read operation. In the beginning, node V has an empty set, CV, that it uses to collect random numbers. Similar to the Blackboard algorithm, node V generates a random number -1 or +1 locally, and broadcasts this value, adding the information that node V is the sender plus a round number. Since there is no Blackboard to read from, node V directly stores its value in the set CV. As we will see, the algorithm works as long as more than half of the nodes do not crash. To reduce the number of nodes that we need to consider in our example, let's just crash them right now. 3 out of the 5 nodes must be alive, so we can crash 2 nodes. Let's call the other 2 nodes U and W. They also have their own sets and, since they received a random number from V for this round, they add it to their sets. Note that the same also happens in the other direction. If node V receives random numbers for this round from U and W, it adds them to its set. Let's get back to the message containing the random number from node V. Every node that receives it not only stores it but also broadcasts it again. Once node V receives its own message again from at least n-f nodes, it concludes that this write operation is successful, that is, enough other nodes must have received it. Note that we always assume that every message is also sent to the node itself, and this message is always received immediately. So, given that there are 5 nodes and 2 may fail, a node waits for messages from 2 nodes other than itself. Once the write operation is complete, node V initiates the read operation by broadcasting a read request. Whenever a node receives such a request, it returns its current set of random numbers. As before, when node V receives n-f sets, the read operation is considered complete. Node V then updates its set by adding all random numbers that it received in other sets. Note that only one random number per node and per round can be added. If there are fewer than n squared numbers in the set, node V proceeds with the next round. Again, let's fast forward a little bit. Let's assume that node V has now just received n-f sets in some round R. It then checks again the size of its set, and this time it is at least 25, which is the number of nodes squared in this example. It then outputs 1 as the result of the shared coin toss if the sum of values is greater than 0 and 0 otherwise. Concretely, let's assume that the sum of the random numbers is 4 and therefore the result of the shared coin toss for node V is 1. Node U adds another random number, a -1, and then gets a sum of 3, and so node U also outputs 1. Lastly, node W adds another random number, which also happens to be a -1, and then gets a sum of 2. Since the sum remains positive, node W also outputs 1 and all nodes agree. Let's now discuss why the algorithm works. Let's consider a write operation. Node V waits for n-f echoes to its broadcast, which guarantees that at least n-f nodes must store node V's random number for this round. Node V will not advance before this happens, so there can be at most one unfinished write operation per node at any time. Let's assume that node V's write operation has completed, and any node W now performs a read operation. Since W waits for the response from n-f nodes, there must be at least one node in the intersection of the nodes that respond to W and the nodes that received V's random number, so the read operation of any node always returns all random numbers that have been successfully written before. So, we conclude that the read and write operations have the same properties as for the Blackboard. The rest of the analysis is now straightforward. Again, using the central limit theorem with the same parameters, we conclude that the probability that the shared coin toss results in a 0 at all nodes is greater than 15%, and the probability that the result is 1 is greater than 15% too. Let's summarize what we've learned. We studied the problem of creating a shared coin algorithm. We then introduced a useful abstraction, the Blackboard, to come up with an algorithm that works. After that, we showed how we can implement read and write operations by simply exchanging messages with the same properties as when using the Blackboard, which shows that we can construct a shared coin in the message passing model. Thanks for watching.